Hello, my name is Jessica Jung,
And I'm Aaron.
and we'll be talking about the functionalities of biomedical implants. Biomedical implants use electricity and magnetism to stimulate and control neuroactivity in the brain, monitoring physiological signals without hospitalization. They can cure diseases such as Parkinson's disease and epilepsy through electrical and optical simulations. Biomedical implants also have neuroscientific applications such as monitoring brain network connections, treating diseases, and restoring sensory functions. In a 10-year study, 60% of patients survived the full 10 years after pacemaker implementation, while the average survival time was approximately 8 years.
However, technologies behind existing medical implants are far from ideal. Let's take pacemakers as an example. A battery-powered pattern generator is implanted in the chest, and a few wires with electrodes are pushed through a vessel into the heart to perform the actual sensing and stimulation. While this design is practical, it has some considerable limitations and health risks. For example, the battery needs to be replaced in an invasive surgical process, which is inconvenient for the patient. The wire also presents health risks as it is intrusive to the blood vessel.
Therefore, in order to make medical implants that are smaller, more effective, and most importantly safer, the first step is to completely remove the battery from the implant and use wireless charging technology to power the implant. This way, only a tiny battery-free implant needs to be physically placed inside the patient's body. The wireless charger can then be attached to the outside of the patient's body to continue transmitting power and checking on the body's internal conditions.
However, this doesn't sound very new, as we already have wireless phone chargers everywhere, and the technology behind these chargers is called Qi. Qi charging, also known as wireless charging, uses electromagnetic fields to transfer energy from a charging pad to a device, converting magnetic energy into electrical energy. This is a convenient and cable-free charging method. However, the problem with this is the electromagnetic waves used in Qi charging, transmitted through the patient's body to really reach the implant, must be strong enough to pass through tissue. Since human tissue is made up of mostly water, these high power and high frequency electromagnetic waves unfortunately heat up the water, essentially cooking the tissue like in a microwave. This is extremely dangerous and detrimental to the patient's bodies, as you can imagine. Another problem is that since we want the device to be extremely small and compact, alignment of the transmitter and receiver becomes a big issue. The smaller the device is, the more perfectly it has to be aligned, otherwise there is a significant drop in the already low power.
One potential solution researchers are investigating is related to the use of ultrasound. When transmitting an ultrasound wave, there must be absolutely no gaps between the flesh and the transmitter. This is due to the fact that ultrasound waves don't travel through different properties of matter efficiently. However, a downside of this is that no matter how close the transmitter is to human flesh, even if it's pressed up against the body, there will still be pore gaps, bumps, and pockets of air that prevent the ultrasound waves from successfully traveling through the tissue. This is why doctors apply gel onto patients before they perform an ultrasound. So going back to the medical implant, if the patient needs to apply gel every few hours for the transmitter to function properly, it would get extremely tedious and inconvenient.
This is where a new solution called magnetoelectric, or ME in short, is being developed here at Rice University, combining the best of both Qi charging and ultrasound charging. The basic architecture is that we use two different materials, one that converts electric signals to vibration, piezoelectric, and another that converts vibration to electric fields, magnetostrictive. Together, this arrangement converts the low-frequency magnetic field into electricity through a two-step process known as the magnetoelectric effect. In fact, as you might already know, electromagnetic waves travel at the speed of light. Low frequency means that the device has to be very large. We circumvent this by converting the electrical signal into vibration, which travels at the speed of sound, allowing us to make the device much smaller while receiving sufficient wireless power. Even when the implant is super tiny, like a few millimeters, it works awesome at low sound frequencies below 1 MHz. Meanwhile, this ME technology uses low-frequency magnetic fields while transmitting through air and tissue, so that it can pass through things easily and does not require ultrasound gel. These properties of ME make it awesome for sending power wirelessly. Low-frequency magnetic fields don't get absorbed much by tissue, so that a stronger magnetic field to get more power without safety worries. And guess what? Changing the size of the magnetoelectric device doesn't change how much voltage it makes. Something called the voltage coefficient stays the same no matter the size, so even if we shrink it, it still makes voltage. Here's another cool thing. The magnetoelectric material can affect the direction of magnetic field and concentrate more magnetic power inside the implant, even if it's not lined up perfectly. Using the magnetoelectric effect, the Sims lab at Rice University has come up with some amazing wireless technologies and implants that don't need batteries. They're using this technology to send power wirelessly to tiny implants with a millimeter-sized scale. But that's not all. They've also figured out how to use this effect to send data to these super small implants, enabling real-time treatment adjustments. For example, they can fine-tune the implant's biomedical stimulation for each patient. And they've also made it possible for the implant to send data back to external devices that you can wear, all thanks to magnetoelectric effects. This is really cool because it means the implant and the external devices can collaborate closely for more advanced medical applications like intelligent self-controlled therapies without going to the clinic.